Hi, thanks everyone. I'm Bing Shen from Zhejiang University. Today I will present the work, a new PPML paradigm for quantized model. PPML stands for Privacy Preserving Machine Learning. It's a joint work with my PhD student, Tian Pei and Xiaoyuan, and my boss, Kuiran. So the background is, it's a bit applied cryptography. The background is you have a server who holds a model, you have a client who have a data, and we want to do privacy preserving inference, model inference, not for model training, just for inference. The server holds the model, and for some reason he want to do it as a service. He do not want to share it. And basically, it's what we call weight, W. W is private to S, the server. And X is the client's data, for example, the prompt for generative AI. What they want to do is we want to jointly evaluate what we call M, WX. M is the model structure, and resulting Y, give it back to the client. Okay, and typically we're talking about is a multi-party computation. Of course, in the literature, you can also do it with TEE enclaves and some other method, for example, fully homomorphic encryption. The multi-party computation, in general, you have multiple parties who want to jointly compute a function or evaluate a function, and the function is public. And in our case, we want the function to be private. Well, exactly, the model parameter need to be private, but the function structure, the model structure is still public. So we treat the model parameter as a parameter, not as a data, as an input. In our case, it's a two-party computation, although in the related work in the sorter, we are comparing some of the multi-party computation. The exact challenge what we're looking at is in privacy preserving machine learning. We usually use a fixed point arithmetic. Basically, each number, you have an integer part, you have a fractional part, and if you do multiplication, then the integer part expand, the fractional part expand, then we drop the least significant fractional part, we drop the most significant bits, and hopefully they are zero. If they are not zero, we are screwed, because it's the most significant bit. It affects the result too much. If you drop the most significant part and there's a non-zero element inside, then basically this multiplication, you consider it a failure. Well, in PPML, we allow some of the failure. Does not affect too much on accuracy. But if you fail too much, then the prediction completely goes to disaster. Okay, and in MPC, what we usually do is we do the multiplication over rings. Why rings? Well, because rings usually align with our computer architecture better. For example, if a 32-bit ring, we use 32-bit register, and for the 64-bit, then 64-bit register. So the carryover, the modular, the wraparound can be free. So what we do is when we do the multiplication over ring, we need to do some scale. We scale it a bit bigger to tolerate the fractional part. And when we do multiplication, we do truncate it back. Okay, for example, let's say we have 32-bit. Actually, inside the value is the original value multiplied by 1,000, just for example. Then you have a two value to multiply. Now you need to divide the 1,000 back. And that's division, what we call truncation. And what we want is we should not truncate non-zero values. If it happens, then it's failure. So what we need to do in practice, in reality, in PPML, we put extra space in front. The dark blue ones are all zero, extra space. That it hurts our efficiency, but we have to do it, otherwise we get a failure. Because we cannot estimate what's the value inside when we do PPML. It's just empirical. We do it once, it works, We don't know what's inside in between. Okay. Now, you know that the truncation is actually very expensive. There are two ways in the literature can do the truncation. One is the deterministic way. Basically, you evaluate the truncation circuit over some two-party computation, for example, over GC or some other way. Very, very expensive. Another way is to do so-called probabilistic truncation. Basically means you allow certain probability to occur errors. And the error rate exactly is based on the number of zeros you put extra space in front. If you put L prime bit space, then the error rate is 2 to the 1 minus L prime. Let's say, well, in reality, it's not going to be big. For example, 16-bit, 32-bit maximum. Okay, so, and the truncation is expensive again. Okay, and we hope we get around with the errors. So we are working around with the quantized models. Why quantized models? Well, because currently quantized models are very popular and be used in practice, but there is no PPML, no privacy-preserving machine learning models address them. Why? Let's first look at the quantized models, then I will explain why. The quantized models basically is designed for limited I/O channels and for limited storage. For example, the original, we have X is input, W is the weight, and L is the function, for example, linear function or nonlinear function, and we want to evaluate L bracket W gamma X, okay? W, X, Z output are sometimes in FP32 or FP64, okay? Now what we're going to store, we usually introduce some quantized values in int 8 bits. That's X prime, W prime, and Z prime, okay? Now, when we do it in practice, I'm not talking about PPML, I'm talking about the normal ML. You put it, the quantized value into the GPU, you use a small channel, you use int 8, and inside the GPU, you dequantize them, become flat, become big, and then you do the operation normally. Then you get the result, you quantize it again before you get it out. Okay? So the I/O is limited, the belly is very fat, that's reality. Okay? And in the right corner, it shows how you do quantization. You take Sx, which is a scalar, it's a fractional number, and X is the FP, it's also floating point or fixed point number, and X prime and Bx, these are integer, okay, 8-bit integer. Dequantization, you do the reverse. Okay, now what's the challenge in quantized model in PPML? Well, the challenge is we do, our current architecture does not support quantization and dequantization efficiently in MPC. Why? If you look at the right-hand side, what we're going to do in the quantized version just for multiplication as an example, then that's what you're exactly doing. The first part is int 8 operation, but to avoid wrapping around, you need to leave a certain space. For example, you need to do it in int 16. And the Sx times Sy divided by Sz, this is a scalar, rescaling factor. And this factor is expensive. This is a fixed point factor, require truncation to do it. And then you have a 8-bit offset, take it back, okay? Now, what we are looking at is, in this work, is we find, well, there's certain operation can fit in the quantized model quite well. That's the lookup table. Why? Because the lookup table, well, basically what we mean is we represent every function in lookup table, including the linear function in the models. Well, in models, you have a linear, nonlinear, active function, etc., everything in lookup table. Okay, why? Because it's a quantized model, the input is going to be 8 bits, or 16 bits, or 4 bits. Okay, and the output is also quantized again, going to be 8 bits. So it's going to be very efficient. The table size is just 256. And everything can be done in the lookup table. That's a punchline of our work. And we don't need a truncation. And because it's a lookup table, everything can be done in the offline. In the online phase, just pick one of the spot of the lookup table, and we can hide the internal complexity of the function. Okay, and well, you may say, well, lookup table is like oblivious transfer, a private information retrieval, PIR. What's the fancy of it? Well, we designed a lookup table evaluation protocol, and its online communication is just O1 in cryptographic sense, and log n in the information theoretical science. Basically, you just open the index, and that's it. So what we do is we assume there's a server knows the model, and which means knows the function f. There's a client who need to evaluate the function. That's his private data. He want to do fx. So server knows f, client knows x. Okay. In the offline, they actually not permute. That's not a good word. Cyclic shift the table to R position, and shared. So the shared table cyclic shifted, and in the online phase, they just open x minus R, and that's just an index. And each one of them take the x minus R position of the shared shifted table, and that's their shared value, shared result, and that's it. In the online version, you open one index, that's it. And in the offline, what we need to do, well, it's complicated. We need to not shuffle, it's also a bad word. We need to cyclic shift the table, okay, obliviously. How to do that? Well, there is a work for shared data, how to do oblivious shuffle. We do oblivious cyclic shift n times faster. We proposed a new protocol for that. In the heart of the protocol, we need n minus 1 out of n random OT, which requires something like log n ROT, and then you can use GGM to do it. And basically, what we do, it looks fancy and complicated, and I want to skip it. So the C, they are going to do the ROT for column-wise. And the red column means the column are missing. N minus 1 out of n ROT means the client does not have the red column, okay? And the server has everything in white, so the server has everything. And for the first row, the C shift 0 position. For the second row, the C right shift 1 position. The third row for 2 position, the fourth row for the 4th position. So you spread the red to the almost every row and every column, and then you sum every row together to be U, you sum every column together to be V. Okay. Then they do some shared shift thing. Well, I will hide the detail due to the time limitation. You can look at the paper, but at the end, they will going to share the shuffled table, the shifted table, okay, and share the offset R. Okay, and we do some optimization. For example, in the machine learning, you probably have one input for multiple different scalars like W0, W1, W2 with the same X. Then we can batch them together using one table, and it's almost the same efficiency. And we can also fill the operators. For example, you have a ReLU layer, you have a BN layer, and you have another layer of convolution layer. And we can compress them together because it's a function output linked to another function, output to link to another function. It's because they are all lookup tables. We can fill them into one lookup table, and that's still 1 out of 256 lookup. Okay, we call it convolution prime. Okay, and for performance, well, for 4-bit quantization, I won't emphasize the 4-bit version because 8-bit version is roughly the same amount of efficiency. For 8-bit version quantization, we're about 10 times faster than, for example, the state-of-art 3PCFSS, that stands for function secret sharing, and 2PCFSS, and of course for the Gabor circuit, etc. And for the wine setting, we actually do much faster. It could be up to 1,000 times faster, because our online, I'm talking about the online performance, because our online efficiency is like the plain text version of the machine learning. We only open the index, and the index is the data. It's like you send the data. The exact communication is like you send the data to the server, and the server reply you. There is no any other communication occurred. For the accuracy, well, people says you are proposing for quantized models. Well, it's not fair. They are using full models. You are using quantized models. Well, on the one hand, there's no MPC designed for quantized models. If you use existing technique for the quantized models, they are going to be slower, even more slower. And okay, for quantized models, how accuracy it is, it turned out it's almost the same as non-quantized models. That's how they propose it. That's how the industry already using it. We are not proposing to how to quantize the models, because that's another work. That's orthogonal to this work. We use the already proposed quantized model parameters and do our evaluation. The online performance comparison, well, there's a big difference for the land setting and the wine setting, about 10 times. Exact figure can be found in our paper. And the bottom says our PPML is faster than, for example, Sigma or Krypton, even with GPU. We only use CPU. We can faster than their GPU version. The last slide, takeaway. So first, quantization. There's no good PPML for quantization. Why? Because fixed point truncation is very expensive. Second, we do propose a lookup table evaluation scheme for both linear and nonlinear computations. Basically, everything inside the model. Three, we achieve about 20 to 80 times speed up for all SOTA PPML. Thank you.
Thank you for your interesting talk.